And my audio is clear for you?
Yes, sir. You are audible, sir. You are audible.
Yes, sir. Then we have another 5 minutes.
Okay, okay, sir.
Kumar.
Good morning, sir.
Good
Welcome,
morning.
sir.
Welcome. Ask all the participants to mute their video
Okay,
and audio. And
okay, sir.
only when they want to ask something, they can unmute it actually. In video, if they want, they can open it, no problem. Audio, ask them to unmute. That is
Okay, sir.
because there is some disturbances will be there. Already there is some disturbance.
Yes,
So,
sir. Right. See, sir. Okay.
ask them to mute the audio. Video, no problem. They can be on, no problem. So only when they want to talk or ask something, they can raise their hands and then unmute the audio and talk. And the instruction கொடுத்துருங்க எல்லாரும்.
Okay, sir. Okay, sure.
Best of luck. Proceed.
Thank you, sir.
Good morning, sir. Good morning.
Morning. I will be then and there joining and going because I have another work also. I will be there coming and then there going. Proceed. Sudha is there.
Yes,
Yes,
sir.
sir.
Yes, sir. Good morning, sir.
Good morning. All the best. Carry on. So,
Thank you, sir.
first our FTP arranged by the department. An infant department. Is clear? Just 3 years old department. And we are having more than 500 odd participants means it is a great honor to us. So we should be thankful to all the participants who have trust on us and registered themselves for this 6 days FTP. So take care of all the aspects of this program and we see that it becomes a great success. Okay.
Sure, sir. Sure.
We can proceed with the program. I will be then and there joining.
Okay, sir. Thank you, sir.
Okay. Thank you, sir.
Dear participants, welcome to this 6-day faculty development program. And it is going to start in another 2-3 minutes. I request all the participants to mute yourself. And there will be a time for discussion. After the presentation is over, we will be having a discussion. At the time, you can unmute your mobile and you can ask your questions, or you can, what we recommend is you can post your questions in the chat box, and that will be discussed, taken for the discussion. Okay. So kindly mute your mobile phones. Thank you. Madam Sudha, madam, are you there?
Sir?
Madam, we can wait for 2-3 minutes and
Okay,
then
sir.
we can start, I think.
Okay.
Sir,
Yes,
Kumar,
yes,
sir.
yes.
Sir, resource person கிட்ட சொல்லிருங்க chat boxல questions கொஞ்சம் இருக்கும் at the end of the session. அதை பார்த்து இது பண்ணி clarify பண்ண சொல்லுங்க.
சரிங்க சார். ஓகேங்க சார்.
Okay.
Somu sir, if the participants posted their questions, selectively we can ask, sir. We can selectively we can take the questions to the chief guest and that can be answered, sir.
Okay, sir. Okay, sir.
All other points.
Training has been done. What do you think when there was no
So what is absolute zero?
There was a computer or not?
You know the absolute zero.
Kavikanan sir. சார் இப்ப ஹோஸ்ட் கோ-ஹோஸ்ட் தவிர மற்றவங்களால மியூட் பண்ண முடியுமாங்க சார்? பண்ணிருங்க சார், பண்ணிருங்க. எனிவே ப்ரோக்ராம் இஸ் கோயிங் டு ஸ்டார்ட். ஓகே ப்ளீஸ். Sir, Mahendra Kumar sir,
Yes, sir.
shall we start or shall we wait for 2-3 minutes?
It is up to you, sir. You are the boss.
Okay, okay, sir. Okay, sir. We shall start by 10:05, sir.
Sure.
Wait for 2-3 minutes. Participants are started to joining. We'll wait for 2-3 minutes, then we will start the program, sir.
Sure.
Nothing.
Somu sir.
Sir.
Somu Sundaram sir. Okay.
Wait, sir. Yeah.
Sir,
Tell me, sir.
Program started. Meanwhile, you can take some photos, sir.
Screenshots, sir.
Yes,
Okay, okay,
yes.
sir. Okay. Yeah.
That can be posted.
Okay.
I think now we can start. I think. So, Somasundaram sir, shall we start the program?
Okay, sir. Okay, sir. I can start. I sent messages in this faculty group also.
Okay.
Okay, sir.
No problem, sir. We can start. Let them join later also.
Yeah. No problem, sir.
Okay. Good morning to all. Am I audible, sir?
Yes, sir.
Okay, thank you, madam. Convener, Dr. V. Venkateswaran, Dean.
Kumar sir, what happened, sir?
Nothing, madam. Okay. Convener, Dr. V. Venkateswaran, Dean STC, Resource Person of the Day, Dr. Uma Mahendra Kumar, Assistant Professor, VIT University, Organizing Secretary, Coordinators, faculty members and research scholars of various institutions. A warm good morning to one and all. First of all, my sincere gratitude to Chairman Lion M.A. Vijayamogan, Vice Chairman Lion T. Sedubadi, Secretary Mr. S. Venkatesh, Principal Dr. A. Somu, and Dean Dr. V. Venkateswaran for giving us opportunity to organize this FTP on recent developments in Material Science 21. On behalf of the organizing committee, I take great pleasure in welcoming faculty members and research scholars who have joined with us for this 6-day faculty development program on recent developments in Material Science 21. I am much delighted to see the overwhelming response from the faculty members and research scholars across the country. Progress in material science is always linked to the progress and welfare of human civilization. Future advances in multiple fields of science and engineering critically depends on the availability of advanced materials. Inventions of such materials require strong knowledge in material structure and its properties. The aim of this faculty development program is to facilitate upgradation of knowledge in the area of material science. With this theme, the topics such as fundamentals of single crystal growth techniques and its optical homogeneity testing methods, photopolymers and AIEE active polymers, quantum dots and its optical properties, energy storage materials, powder X-ray diffraction and NMR spectroscopy techniques are arranged to this faculty development program. Today's topic, X-ray diffraction, a practical guide for powder diffraction analysis, will be delivered by Dr. Uma Mahendra Kumar, Assistant Professor of Physics, School of Advanced Sciences, VIT University, Vellore. Dr. Uma Mahendra Kumar received his PhD in physics from University of Hyderabad, India. Currently, he is working as Assistant Professor in the Department of Physics, VIT University, Vellore, India. His current research interest is in the X-ray absorption spectroscopy and ferromagnetic material. He is involved in modeling of materials using from his experimental investigations. With this brief introduction, may I now invite Dr. Uma Mahendra Kumar to deliver his valuable speech. Please, sir.
Good morning, everyone, and many thanks for a kind introduction, Dr. J. Kumar.
Thank you, sir. Thank you.
Yeah. So, shall we start? We will go ahead of this.
Yes, sir. Sure, sir. You can start, sir.
Yeah. So, today's topic of discussion, I would like to put it like it is diffractometry, which means we will be concentrating more on how to do the diffraction experiment. Usually, this part of experiments, majority of us don't have the opportunity to do by ourselves. Usually, we give away our sample and wait for the data. But once the data comes, what happened with the sample inside the diffractometer, nobody knows. If we know those details, what is there inside the diffractometer and which way it affects our results, then it will be quite comfortable for all the researchers who are new and who are seasoned researchers, and people who are experienced will have a little bit of comfort. And whatever I am going to present today, all these topics are well known to all of you. So I consider this as just I'm going to like a refresh and remind you that all these things are still there. We need to give more attention to these details, especially when we are analyzing the data coming from nanomaterials. Exactly from everyone, whoever is involved in material science at some part of time or in one or other project, we must be dealing with nanomaterials. So in this lecture, I first give you a little gist of what nanomaterial is and how we can use X-ray diffraction to characterize the structure of nanomaterials. And at the end, I will talk about what is the possible errors people make in interpreting the data. So this is going to be like a mix of experiment as well as analysis. If any doubt comes, I feel like you can immediately ask me, but of course, Dr. Kumar mentioned that you should ask at the end. It is my request for Kumar saying that you please allow people to ask me. Otherwise, it just goes like a radio program.
Oh, sure, sir.
Monologue.
That's your wish, sir.
Yeah,
That's
I
your
will
wish.
be happy to answer then and there. If at the end anything is there, which needs a elaborated explanation, I will do it at the end.
Okay, sir. Okay.
Right. Thank you very much. So this is, as I mentioned you, this is the outline of my topic. We will see what nanomaterials are, what nanostructures are, and then crystallite size and grain size. This variation why I want to show you is in the papers when student is started writing very first year or second year of their PhD, they don't differentiate between particle size, crystallite size, and grain size. They are all different things. So I would like to give a small definitions there such that people have a understanding of that and how the diffraction is going to be affected by. Usually there is no issue with nanomaterials, but because of the advent of nanomaterials, diffraction has been misunderstood since long. So those misconceptions I would like to sort it out. And then size and strain analysis. This is the most interesting part for majority of the researchers. So I am going to include this part and the care needed when we are doing the sample preparation, how the sample should be given, how much of the sample should be given. Okay, and what kind of care is necessary when we are measuring the diffraction. What are the other things which are really involved, which gives you, even from the bulk material, you can show that it is nanomaterial just by changing the arrangements in the diffractometer. I will show you how that happens. So there are two things in nanomaterials. So the one is anything which is less than, this is just a thumb rule. So if somebody asks me what happens to 101 nanometer, there is no answer for that. But it's like a thumb rule. You can say that anything which is less than 100 nanometers can be considered as nanomaterial. But when it comes to the nanostructures, it is purely based on the confinement. Students who are just now studying are the faculty who have already dealt with quantum physics. You know that it is always dependent on the confinement. The confinement is one-dimensional confinement, two-dimensional, and zero-dimensional. We will see. So these confinements will give us thin films where we will see the size effects. One-dimensional means we will have nano wires, ribbons, and other things, and nanoparticles, which are the quantum dots. Usually, this is the one all the material scientists will be concentrating more on this, which are zero-dimensional objects, where charge carriers are confined from all three dimensions. Okay, so we are going to deal the nanoparticles part. However, we must understand this confinement, whatever we are talking, it got to do only with the electrons, electrical properties and optical properties. Structure got nothing to do with that. They are very, very small size of particles where number of lattice planes are small. That is what more concern when we talk in terms of X-ray diffraction. So this is the difference. Usually several students ask this question when they do a SEM, scanning electron microscopy, they will see different size, and when they go for X-ray diffraction, they will see different size. Why it is happening means in the SEM, we will usually see this particle sizes. They are from the morphology from the surface. And this is the one. So this can contain several crystallites which are oriented in several different orientations. When X-ray is going to measure them, it will measure only this part. So now you can figure out why from SEM we will have larger particle size, and when it comes to the X-ray diffraction, it comes why it is very small. Right. So in X-ray diffraction, they define them as coherently scattering domains. It is no way. Crystallite size is a very loose word. They say coherently scattering domains. So these domains can have a width, these domains can have volume, these domains can have height. So when we go for detailed analysis, we can do this size, which is volume averaged, and we can have area averaged sizes also. But if anybody can do TEM, that TEM result is going to marginally or excellently agree very well with XRD. So that is the reason in our papers, when we submit to the journals, they keep asking for TEM results. So TEM is the one. But if you do a nice analysis from X-ray diffraction, you can always avoid TEM analysis. Okay. So now, what kind of information the diffraction is going to give us? This is a general trend. I am just going to put it. Here I am showing only 2 peaks. Frankly speaking, there will be several peaks, but for our comfort, I am showing only 2. So this is the data recorded on cerium oxide sample. So, and here we are having this peak. The blue line is going to represent the peak maxima, or you can say it peak center. So this peak positions, not alone one, every place, the peak position is going to determine the Bravais lattice of the material, whatever Bravais lattice it is. And then the peak heights, otherwise we can say that intensity of the peaks is going to tell us positions of the atoms. How this is related is because of the atomic form factors. If you have oxygen, if you have cerium, they have their own different form factors. Together they will give you the height. Now inside the cerium, if I add a little bit of hafnium, then obviously this height is going to be either increase or decrease depending on where the atom is sitting. Let us suppose this peak belongs to 111 plane. I am assuming here people know these Miller indices and other things, right? So this, if the atom, the dopant atom, the hafnium, is sitting in 110 plane, obviously this peak would have been affected. So when we are comparing our experimental data with the JCPDS standard data, I am sure everybody must be writing this. We have to see whether the intensities are matching or not. Even the relative intensities, they should match. If they are not matching, means there are several reasons. There are several reasons why intensity of the peak is affected. So in the entire talk, you could able to see there are several places I will talk about where the intensity is getting affected. So whenever in your X-ray diffraction experiment, you lost the intensity, means we should be able to rule out all the other parameters except the sample ones. Then if we could able to avoid all of them, then we can interpret loss of intensity only to the sample. Right. So here intensity is atomic positions, and the peak area, the area which is covered by one single peak, it belongs to the phase content. Suppose if we have two different materials, let us suppose cerium oxide plus zirconium oxide, I have added together, they both can have similar place, similar kind of a peak, but if two materials are there together, their peak intensity is going to be very, very different. So when we do this quantitative analysis for X-ray diffraction, then we should be able to see the peak area which belongs to the phase content, how much amount of particular phase is available. And next one, which is more interesting for us, is the peak shape and width. So this peak shape, people usually, when they want to use Scherrer's formula, we will find FWHM. When we find this FWHM, we will use a Gaussian peak to fit this. Whether it is fitted properly, whether it is not fitted properly, nobody bothers. We just bother about FWHM. But these peaks are having shapes, and every shape has, there is a meaning, physical interpretation is there, which has been correlated to the shape of the crystallite, defects in the crystallite or faults in the crystallites, strain in the crystallites, everything you can interpret from the shape of these peaks. So this shape of the peak and its width is going to be, we can get crystallite size, its strain, defects. The easiest way is the Scherrer formula, which I am going to show you. And before going there, we can just see, people used to ask me how many number of peaks are necessary to be measured. Okay, fundamental answer and correct answer is as many peaks are possible, we should be able to measure, but all the time it is not possible. Then what we give a thumb rule is a number of peaks over crystallographically independent atoms. Like if you take nickel oxide, let us suppose nickel oxide is cubic and the unit cell will contain only 2 atoms. I means primitive cell will have 2 atoms. So nickel and oxygen, just 2. So number of peaks over number of atoms should be 10. So obviously we should be measuring 20 peaks. That is the requirement, theoretical requirement. Then only we can say that this is the phase. But usually when we go for simple cubic materials, those many peaks will not be available in the available measurement range, 2 theta range. So in those cases, we can accept them. But whereas for low symmetry, which means after hexagonal, if it is tetragonal, triclinic, rhombohedral, these kind of phases, we should be able to measure large number of peaks. Okay, so this is very, very essential to have more number of peaks. With one single peak, nobody should phase identify whether this is cubic or hexagonal. This trouble comes when we see thin films. The phase identification of thin films, usually thin films thickness is going to be in few nanometers, maximum half a micron, which means 500 nanometers. Then crystallite size will be very small, and usually they will be oriented in one preferred direction. So in that case, we will be able to see only one peak, in rare case the second peak. In those cases, we should find another way to figure out what kind of phase this is, like TEM analysis and other things. But when it comes to the story of powders, we should have as many as peaks possible to measure. Now, we will go for the size calculation. The easiest method is Scherrer's method, and then Williamson-Hall method. Where an hour back, I am not going to deal very detailedly, but I will show you what is the necessity and why we need those things. And then peak profiling, hole pattern fitting, these two are also there. I just wanted to listed them you to know, but they are interesting. Each topic is another lecture. So this today we will not do those things, but first three we will do briefly. So this is the Scherrer formula, which everybody knows. And here students will have this question, why this K value, K is a constant, Scherrer constant, it has a given value of 0.94, why so? So it is not a constant technically. It is going to vary with shapes. Every time we change the shape, the Scherrer constant is going to be different. But safest one is spherical crystallites. Why we are more interested in spherical crystallites means, at least for all the physicists, it is most interesting one. One of my professor used to tell me that if you just give a cow to a physics professor, he can write an equation for that. How? Means we can assume cow, the whole major part of the cow is spherical, rest of the things are simple deviations from that, 4 legs, 1 tail and a head. These are just so gross part is spherical, so we can write an equation very easily. So same philosophy people have adopted here. So what they say is, if it is a spherical crystal, rest of the things are small aberrations or outcomes, where we can give 0.94 as a safe value for the Scherrer constant. But when we go for afterwards, people have done a lot of research on this and they have mentioned this. However, Scherrer formula is going to give us either overestimated or underestimated values, because Scherrer is not going to bother about how much strain in this sample, because entire broadening is given only in one single parameter here, beta. The entire FWHM, we will put it over here, but peak broadening happens for several reasons. Whatever we know, simply if you want to put, one is instrumental broadening, crystallite size broadening, and strain broadening. But when we calculate the crystallite size using Scherrer's formula, we are attributing entire broadening is just because of the crystallite. So that's the first gross approximation. And the second one, when we go for that, another approximation is the instrumental broadening. Usually what we do is we just subtract a constant value. some 0.01 from the all FWHM. But this has to be done in a perfect way. I will show you that also. Right. So this is people who are just playing with the crystallite size. This is a blog where you can simply give this. This is your wavelength, peak width, and then the peak position. If you give those things, it will nicely calculate crystallite size and strain. If you guys are aware of this easily, it is available online freely. Anybody can use that. Right. So the next one is little bit sophisticated when compared with Scherrer's formula. It is, we can nicely separate out the contribution of strain, contribution of crystallite size using Williamson-Hall method, where we are going to plot beta or cos theta and about sin theta. Theta is your Bragg angle. Okay, and this is going to give us, the slope is going to give us the amount of strain, and here we will have k lambda. Again, k is going to be the constant, lambda is our wavelength, L is our crystallite size. We can easily calculate and separate out. But here in Williamson-Hall method, we can't use all the peaks. It is going only in one direction, but we have to use a family of peaks. Like you can start with, let us suppose you have 111 plane, then you can go for 211, 311, 411, or 222, 333, only a family of planes you have to use. You can't use all of them, or otherwise you, for every different family of lines, you have to plot it differently. Then it will show you a different sizes and different strain values pertaining to a particular set of Miller indices or lattice planes. So there is no a single answer for the entire sample. This is my average crystallite size, this is my average strain. You will not get it with the Williamson-Hall method. In the Scherrer formula, you will get an average crystallite size, but it is purely a huge gross approximation. But Scherrer formula is surely it is useful when we want to see a trend. Let us suppose you are having a material and you are using it for you are doing a heat treatment, and you want to see whether crystallite sizes are increasing or decreasing. So it can show you the trend without details. It can show you the trend. It is qualitative, increasing, decreasing, anything that can show, but you can't bank on interpreting all the results based on Scherrer formula. Right. If people are agreeing with me, or you are not agreeing, you have questions? Well, I will go further. This is also another.
Professor, I have a doubt here.
Yes, sir.
Is this the only way of determining the stress associated, strain associated with the particle, or there is some other method by which you can calculate?
Yeah, there are several methods, sir. However, it is we have to do the profile fitting only, purely. But this profile fitting has its own advantages, means pros and cons. How this goes is the effect of strain should be propagated throughout the sample, or this strain is alone, it is there in one particular crystallites. Means the crystallites which are oriented in one particular direction, those are only experiencing everywhere it is there. So it depends on which peak you have chosen to analyze this. So what people have done is, instead of getting confused with the different peaks, let us analyze everything in one single pattern. So that is something people call it whole profile fitting.
Okay,
So
Professor.
they use all the peaks in order to do that. But these ones are till now what I explained, Scherrer as well as Williamson-Hall, it is peak by peak.
Okay, Professor.
Yeah, and here also we have several issues like alpha 1, alpha 2. Students never bother about there is an alpha 2. If they see a broad peak, they will fit that with one single Gaussian, and they say that this is that broad, but they have to see there is a alpha 2 contribution in the X-ray diffraction. When we do first we have to strip out the alpha 2, then we will have the real widths, then we should come. So these are the care we should need to take. Whether alpha, some of the diffractometers still have beta also, which means on the left hand side also you have certain amount of broadening, but that we will know only when you have a diffractometer at your hand. But majority in India, we just send a sample out and get the data. So those are the practical difficulties we have.
Thank you, Professor.
So we will just sort out what are the possibilities where instrument can contribute to the broadening. Forget about the crystallite size and the strain. Instrument itself has a broadening, and this broadening is not a constant, because in the Scherrer formula we say that just subtract the instrumental broadening of 0.01 or 0.001 something, and we will start calculating. But this width is not a constant. It varies with the 2 theta values. Here I have shown, I couldn't get a picture with the 2 theta values, but this is 1 over. This is Q values. This is alpha by sin theta, Q is. So here you can see that small value means larger 2 theta value, higher values means low 2 theta value. You can see this is Gaussian widths as well as Lorentzian widths. The blue one is Gaussian plus Lorentzian. You could able to see them, but all of them will have similar kind of a trend. So these widths are very large at higher 2 theta values and small at lower 2 theta values. Based on this fact, if somebody is using Scherrer formula, you should be using the peak which is at lower values, not at the higher values. If you are using a peak which is at higher 2 theta, then we are introducing the broadening which is coming from the instrument, but it is not from the sample itself. So the sample instrumental broadening will be small at a lower 2 theta. So only those peaks you can consider for analysis when you are calculating the size or strain. All right. So other ones, what are the things which are going to contribute more for our instrumental broadening? It is this is the schematic diffractometer, where you could able to see we have the source, we have a detector. These things are not going to change our life much, but we have here something called receiving slits. On this side we have divergence slits, and this solar slits. These solar slits are just meant for creating planar waves. The X-rays which are coming, they will make it like planar waves, nothing more than that. But divergence slit and receiving slits, which we never bother about, those things are going to be affecting our peak broadening largely. We can see those things. So this is the receiving slit, what we are going to see. And I am giving here the size, how much it has been opened. This is 0.1, here 0.05 and 0.2. You could able to see the resolution. In the first case, the resolution is poor but you have intensity, large intensity you have. But if you want a good resolution, it is available at 0.05, but you lost the intensity. If you open it, if it is a large one, you have good intensity, but you lost the resolution. Means alpha 1, alpha 2. Here we are talking about only one peak, but if you take anything like hexagonal, let us suppose zinc oxide you are taking at very lower angles between 20 and 30, we will have a triple peak in zinc oxide. People whoever has worked, all that will become one single peak. And people think that it is because of the small crystallite size. I have a nanocrystalline zinc oxide. It is not true. It is because of the diffractionist, whoever is measuring, he has used a large receiving slit on the detector side. So how we can control this? We can control this by giving us our own set of instructions for the diffractionist, what we need. Otherwise, we will have serious trouble in interpreting our data. So all of them, these are now, you can see they are at different angles. You can't figure out. If you plot them together, you could able to see here, instead of width, here it has been given in angles. You have a smaller angle and larger angle. So when it goes to the angle is large, you will have a broad peak. It is just because of the receiving slit. It got nothing to do with your crystallite size. So we have to choose the right experimental setup in order to get the right data and our interpretation further. This is anything new. All these things are already there. You can see this is a book. It is Modern Diffraction, Powder Diffraction, written by Jenkins. You can find all this information there. So the other one is divergence slits. This you have very much aware of these things. You might have seen when we give the sample, powder sample, what a diffractionist will do is he will pour it onto a glass plate, load it onto the diffractometer. But when he is pouring it onto the glass plate, how big he made that. So it depends on what is the footprint of the X-ray. So here, whatever you are seeing, this gray, this dashed lines, this is the area of your material. The rest is your sample holder. At a particular angle of theta, which is 40 degrees, we are seeing only the material. But when it decreases to 20 and it is further decreases to 10, we are seeing the sample holder also. So in that case, first thing is we will lose the intensity. Second one is we will get the diffraction peaks from the sample holder. Usually it is a glass plate. In some other places, it will be aluminum plate. So we should see when a new peak is coming, people think that next phase is coming. We have to first rule out the peak is not coming from the sample holder. This is the problem of using wrong size of divergence slits. So when we are asking for this one, we should ask 1 or 2 trial runs where it can give us the exact or the required divergence slit width. Any questions here?
Sir, good morning, sir.
Yeah, please, sir.
Is it possible to reduce that divergence slit before
Yes,
the or,
yes, there are two things nowadays in new machines have come because if you see the diffractometer which is coming from Philips, sometimes the sample holder moves. It rotates along with the detector. Sometimes it is stable, and then we were tube as well as detector moves. So these are two configuration. One is theta to theta motion. Another one is theta theta motion. In this theta theta, you do not have any trouble. Easily it will be going up and down. But when we go for theta to theta, it is moving because your sample also moves, then footprint is going to vary. So what people have done is they have a automatic divergence slit. For higher angles or lower angles, accordingly the divergence slit width will change. So a large amount of intensity will be coming in. That's why at higher angles we could get some intensity. But this is effect of divergence slit is a little less, but the receiving slit information should be more. That should be automatically increasing such that at higher angles you should have good intensity. That is my opinion. But this is in your hand. You can always change. If you go and see the diffractometer, these are not very difficult ones. They are just small slits like what we see them in our spectrometer, which you can with a screw you can increase and decrease. But in diffractometer, you can insert a different size of a slit, half degree, 1.5 degree, like that it will be there. Which one is more suitable for your sample? You should use that one. A trial run is always necessary before you do a what do you call a standard measurement. Any other questions, sir? Right. So apart from size and instrument, we will have the other part, which is because coming from the strain, and strain is simple strains we can have, which we could able to see transverse, compressive strains. Okay, these strains are going to simply shift the peaks. But whereas the lattice distortions, which means let us suppose we lost one atom, then the lattice is distorted. We have an extra atom coming, then lattice is distorted. When I say lattice distortion means your D-spacing has increased or decreased. So these ones are going to give us again peak broadening as well as peak shifting. So these two things we have to see together. So how we can formulate them is we have to bifurcate. Williamson-Hall method will not be able to do this, but we have to do Warren-Auerbach method, which is based on integral breadths, which can separate out the contribution from the strain, contribution from the crystallite sizes, and when it is when it is separating out the strain values, it will show you how much it is coming from the dislocations, how much it is coming from the faults. But this distinction only experimentalist only he knows, who knows the history of the sample. If I have a sample with more number of dislocations, I should attribute this effect to the dislocations. But if it is more of faults, then I will attribute to the fault. So there is no straightforward definition for what is contributing to what. But this can be done with Warren-Auerbach method, where you could able to see this is the surface domain size, which means here I have in the y-axis we have the frequency, which means how many are there. Then you can have this question, what do you mean by how many are there? Which means here it will talk about size distribution. It is not about average crystallite size. It is talking about size distribution. So in a sample, now it gives you the full picture. In a sample, it is not going to have, and let us suppose I have 30 nanometers of crystallite size. It means that is an average size of 30 nanometers, but inside it will be having a large distribution. There will be crystallite size which are much larger than 30. There are crystallite sizes which are much smaller than crystallite 30 nanometers. So this is the distribution. Now here what we are seeing is one is surface weighted, which means it is area weighted. Over the top of the crystallite, if you have, let us say you have a hexagonal crystallites are there, on the top how big they are from the top if you see, and other one is volume weighted, total three-dimensional volume crystallite, how it is varying. So in both the things you can get it from Warren-Auerbach method. If this is the site where you can see, this name is Devar Balger. He has created this program where you can conveniently calculate these distributions. These distributions will match the results from TEM. You can see that part too. You see, this is the distribution which is calculated from the breadth program, and these are the bins which are coming from TEM. So it gives you a full picture from just X-ray diffraction. But only thing is we need to do a good amount of analysis. If this kind of information, if you give in any of your paper, then people don't have a question about asking about the crystallite size for you. Amma, any question, Amma? Fine. Right, sir. So there are other methods, other errors, which I just want to, and with these errors, I think I could able to finish this. First thing is the flat specimen error. This one, I think by now you can understand. I have already given you the example of when we put the glass plate over the top of that, if we put the powder. So when we put this powder, how thick it should be. Usually I used to see people used to send tiny vials where you can it is not even you so enough for sniffing what powder it is. That kind of tiny amount they will send it for X-ray diffraction. That amounts are never ever suitable, and whatever the results we get from that is not suitable enough. We should send a minimum of 1 gram of sample, and sample holder should be filled with this powder tightly. Otherwise we will have density problem will come. Porosity in the sample will give you spurious peaks. So we should give enough amount of powder which we are going to fill the entire sample holder. And sample surface should be smooth, completely smooth. If your sample surface is, let us suppose if somebody is using metal alloys, it should be mirror polished. Then only diffraction gives good results, or else chemically it should be etched. People used to say that it is not so necessary. If you not so necessary, then you must be interpreting your results wrongly. There is no reproducibility. The first one is flat specimen. Why? What happens, sir? What happens means your focusing circle, which has been focused, means the X-rays which are coming from the X-ray tube. This is the filament we are talking about, X-ray tube. The line which is coming here and then goes to the detector, which is falling in one circle. When your sample is displaced either up or down, the focusing circle means this both filament and as well as your detector, means X-ray source and detector, they are not in the same focus. Then obviously first thing is we will lose the intensity. If anything is measured, that is going to be distorted. And how much we can see is, it has been given a formula. You can calculate and see how much variation you will get based on how much you are off from the flat surface. The other one is specimen displacement. This specimen displacement problem will come only with the diffractometers where sample is going to move along with the detector. If sample is what do you call, it is not moving, is going to be fixed at one position. In that case, like theta to theta measurement, you don't have this displacement problem. But when it is moving, usually the glass plate, if it is not fixed properly, it will slightly will tilt, and every tilt will move your peaks either left side or right side, and we will start interpreting them as strain in our samples, but actually there is no strain in our sample. So this has to be checked again and again in order to in order to avoid the wrong interpretation. The next one is large set of students ask. Yes, sir.
In previous calculation, what do you mean by R, sir? Capital R?
This is the radius of the goniometer, sir. This is going to be constant engineering, how it has been engineered. So what is the distance between source to the sample, and it should be the same. So sample to the receiving slit, that is the R.
Okay.
So the student used to ask, what should be my step size? If he has a good friend at the diffractometer, he will use.
Sir.
Yes, sir. Yes, sir. Yes, sir. Please, I am listening. You can ask the question.
Sir, in previous equation, sir, there is cos theta, sir.
Yes.
Sir, I don't understand this angle, sir, cos theta.
Cos theta,
in equation 7, sir, 2s cos theta by
yes.
r.
Yes, yes, sir.
Yes, sir. Then in this equation, cos theta angle, I can't understand this angle.
Oh,
sir.
This theta angle belongs to the receiving slit. Receiving slit will
Yes,
be
sir.
given the angular, angular opening of the receiving slit. How much is the theta?
And sir, the dependency of theta, sir, what will be the effect on this specimen, sir?
Your sample, your peaks will be displaced, because it is simple. If we go to the optical grating experiment, we would have done
Yes,
in
sir.
your earlier classes. If we
Yes,
just
sir.
move the grating, or we just tilt the grating, all your peaks will be tilted to one direction. Distance
Yes,
is the
yes,
same,
sir.
but we just tilt the grating, all your peaks are moved.
Yes, sir. Yes, sir.
Either we changed the source, nor we changed the screen, we just tilted the optical grating. So that
Yes, sir.
affects the same thing. If we this sample is not sitting at a proper place, which is going to shift your peaks, that is we can interpret all the time. We will be interested in, yes, whether there is a shift in the peak or not. It says yes, because of this sample displacement, we will see a displacement in the peaks, and we interpret this as tensile stress or compressive stress, something we will do that, but which is not actually it is having. If actually it is having means we should be able to reproduce, but multiple times who is going to measure for us? That is not so easy. But people who are having a diffractometer at hand, they should see. But
Yes,
this sample displacement is an adjustable parameter in the analysis. When we go for full profile fitting, we will adjust this. We could able to shift the entire, we can calculate and shift this entire pattern in one direction, not one peak, one entire pattern, you can shift it.
yes,
This can
sir.
be done.
And sir, if we increase the radius, sir, then sir, what will affect the specimen, sir?
Same, I will go back to the same experiment. Now you are increasing the sample, optical grating to the screen distance. Then your spots will be moving further apart. Then all your peaks will be spreaded all over the 2 theta.
Yes, sir.
Then this is not because of the sample. This is because you have changed the R.
Change. Yes, sir. Yes, sir.
Yeah.
Okay, sir.
Yeah. Now the question comes is about what is the step size? The step size is usually people ask how long I have to measure or how many steps I have to measure, whether it is a step scan or continuous scan. So the difference between step scan and continuous scan is pretty simple. It is the electronics which is behind the diffractometer. Otherwise, both are just step scans only. In the continuous scan, you don't have a control about where you are collecting the intensity. It will just collect randomly throughout the range, and it will put the points according to the software you gave. But when we go for the step, then for every step, it will stop the diffractometer moving and it will collect its intensity. It is depending on the nature of the sample, we choose whether it is a continuous scan or step scan. What is the advantages of continuous scan? Continuous scans we can do for trial runs. Let's suppose I wanted to see whether a particular phase is available in my sample or not. Then we will do a continuous scan, which you can finish in just 2 or 3 minutes. If you give 10 degrees of range in 3 minutes, you can finish. If you have the phase, you can measure it properly. Otherwise, you can discard the sample. So for that purpose, continuous scans are good. If you want a serious analysis can be done for the sample, then we should go for step size. Step scans. And when we go for the step scan, people will ask this question, what kind of step I should use? 0.01, 0.02, 0.05 or 0.1, which one? So people have given, you can see this from this paper. It is a little old paper only, 94. You can see here, this peak is having the top point on the right hand side. This is the top. When I say top point, it is the maximum intensity point. Okay, so you should define the step in such a way that this maximum intensity point stands in the middle of the peak. So for your sample, you have to fix, once you have to measure it and see what are the different types of peaks we get when we measure. I can show you here. See here, this is flat, means we don't know whether this is the maximum or this is the maximum. This is the worst way of measuring it. This is the best way. The B case, this is the best way, and C and D are okay. We are here taking a risk of a little bit of uncertainty, but in the B case, it is correct. So when we are measuring, the step size should be in such a way that this peak, which is on the top, should have more number of points to define this curvature, and less number of points here in the inflection. That is not a problem. But again, near the tails, there should be large number of points. So then it appears that the peak, the step size is not going to be a constant. Okay, so in automated diffractometers, there is a variable step given for us. We can measure accordingly, or otherwise one peak anybody can measure like this. It won't go beyond 5 degrees. So you can measure this and find the number of steps properly, which gives you this kind of a sharp peak, and use the same step for entire diffraction. All right, sir. For step size, is there any other question?
Sir, good morning, sir.
Sir.
The step size will affect the crystalline size or strain, sir?
Certain extent, yes, sir. Because if your peak is not properly known, the area under the peak is underestimated. The crystallite size is purely coming, the FWHM, whatever you are calculating, is coming from the area. If area is underestimated or overestimated, it is going to affect your crystallite size, as well as these tails. How far these tails are going? This is a very important question. You have raised it up. I forgot to mention. Profiles, when we fit them, usually people fit it for a Gaussian or Lorentzian. If somebody is known, they will use it with YZ. What is the advantage of YZ function is it is a mixture of Gaussian and Lorentzian, which is very close to the diffraction. The diffraction peaks we can comfortably model much more conveniently and accurately with YZ function. Another one is pseudo YZ function. So these are the spectra where you can, at the end of my presentation, I will show you one more software piece which I liked a lot, that I will show you. Then you can appreciate this one. The tails has to be properly fitted, then your crystallite size is going to be accurate. For your question, answer is yes. If the step size is different, it affects the crystallite size as well as strain. Simple answer. Any question? Other questions, sir? Oh, good.
Sir, I have a question, sir.
Please, sir.
Sir, most of the time when a research scholar goes for a XRD investigation, they don't know what is the suitable size or appropriate step size for their sample. In that occasion, what is the recommended step size for most of the nano samples, sir?
It depends, sir. If I will give you the best case scenario is assuming that you have a fully crystalline sample.
Okay, sir.
Then 0.02 will be a good step size.
0.02.
0.02.
Okay, thank you, Professor.
If it is not crystalline, large amount of still amorphous nature is still there, then we should go for 0.05 or even 0.1, because the more the steps you are increasing, or you have a very small step, we are contributing more to the noise rather than to the peak.
Okay.
And the second point is acquisition time. Usually for every step, they will give 1 second time, which is no way sufficient. So my usual what I used to do is we will take where we have the prominent peak, first observation. So that will span around 3 degrees. So we will do for different step sizes, 3 scans with different acquisition times. So you give 1 second, you give 3 seconds and 5 seconds. So with every time when you are increasing the acquisition time, the intensity is going to increase. At the same time, the definition of the peak is going to be very, very different. So in these 3 small scans of one single peak, you will find the best possible one. And then you can use that setting for entire spectrum, and you will get a very good spectrum. Otherwise, we end up seeing whether it is noise or peak, we never can distinguish. But still, student will be able to see a peak there, and we will try to convince you, yes, sir, there is a peak. So that is just because of a human mentality. Otherwise, there is no peak there. Right, sir.
Thank you, Professor.
Right. When we prepare these samples, how we should prepare them? For that, there is a good amount of explanation was there. Here I will put it like briefly. When we are making this powder, before going to the diffraction, always we should grind it and use some kind of a sieve in order to get a very smooth powders. What kind of smooth? A smoothness should be like our talcum powder, what we used to apply on our faces. That kind of smoothness should be there. There should not be any granular particles. If we have a granular particles, as in the case of this second, you can see in the red box we are seeing the particle size is much bigger. Bigger than, how much bigger means bigger than 40 microns, 50 microns you can say. And the other set is which is less than 40 microns. You can visibly see that when size is more than 40 microns, which are not grounded well, you could able to see the intensity has drastically affected. Why this happens? Why we are seeing this kind of loss in the intensity is because powder diffraction is entirely based on randomness in the orientation of the crystallites. When the crystallite size is big, the randomness will not be available for them. All of them will sit in one particular direction, and we will be either we are measuring in that direction or not, we don't know. So rest all peaks, we will have this small intensities. We think that material is not crystalline, but in fact it is not grounded well. So we should use a mortar and pestle and make it like very fine powder before giving it to the diffraction. Then students, there are some very enthusiastic students, what they do is they ground it too much, and we will be going below 1 micrometer. 1 micrometer, below 1 micrometer when you go, they will gain some amorphous content inside that, which is not actually in the material, but because of our grinding it has come. So then the effect of crystallite size, the strain, everything will come into picture just because our student has put more effort in grinding it as a smooth powder. So there should be a balance between how good we have to grind it, how much we have to grind it. That's why people say for the touch, it should be like a talcum powder. Then we can always, it is less than 40 microns. It's a good powder for diffraction. Yes, ma'am. Right. The other case of problem is preferred orientation. This is a major problem in thin films, but in the powder case, it should not be. Where you could able to see here, this is very randomly oriented. There is no preferred orientation in this sample. So we will have nice peaks which we got. But because here you could able to see the crystallites are not grounded well, number one. Number two is they all are arranged in one particular fashion. Then they will give the peaks completely at a different way. And if you turn this sample of another 90 degrees, you will get another peak more intense. So every time people load it, you will get different results. That is because it has a preferred orientation. Some samples are there which grow preferably in one particular direction. For them, nothing can be done. But usually for powders, you should grind it properly and measure it. If you have the doubt of preferred orientation, my suggestion is just as I told you, turn the sample in 90 degrees in one more direction, measure it again. Then obviously you can see if there is an intensity change, you will know that your sample is having preferred orientation. Regarding this, any doubts, sir? Preferred orientation now. Right. Here I just summarized all these different kinds of errors. So first one is absorption part. So then, which means sample is absorbing. If you see, we are using a copper K alpha, and if we go and use iron sample, then we will have this trouble. The entire it is going to absorbed by the iron. Or if you use copper, you will have trouble with copper samples with a copper target. So this is because of it is absorbing. And other one is, and what happens is you will lose the intensity. Preferred orientation is you don't have enough amount of randomness, means you did not grinded it properly. So certain peaks will lose their intensity. If you overdo it, then we will have sorry, not overdoing it. If you have a you give very small amount of powder to the diffractionist, then we will have small number of crystals. Again, you will lose the intensity. All these intensity fluctuations will never be able to reproduce. So your interpretation is completely ambiguous. You don't have any control in your interpretation. Next one is if you overgrind it. Below 1 micron, if you overgrind it, all the peaks will broaden, certain amorphous content will come in, contamination will come into picture. This contamination will not come if you are doing mortar and pestle, but in some labs, people use a tiny ball mill where they overdo this milling. When we overdo this milling, the balls which you used for milling, certain amount of that material will come into ours, and then we will have contamination. Other one is amorphization, which is not actually in our sample, but when we grind it more and more, we will make it amorphous. It will lose its three-dimensional ordering. The long range ordering will be absent, and it becomes amorphous. All these are made by the user which is not actually in the sample. So all this care we should take before we go for the diffraction experiment. I believe with this I will stop boring you. Now you can ask questions from anywhere to anywhere.
Sir, slide number 28, sir.
Yes, sir.
Okay, here you told we can rotate 90 degrees, no, sir. That suppose if you are getting a different peaks for different rotations, means then how we should consider which one is correct?
It is having preferred orientation, sir. Your sample is oriented. You see, sir, here in the cartoon I have shown, these are grounded particles, which are almost like spherical. But whereas here, these particles are grown like bananas. They are elongated ellipsoids, which means that could be because of your material is growing like that. That is material property, which we can't change anyhow. But other way around, when we do this solid state reaction and other things, they have grown like this. Okay, so this is the shape property. If you grind them properly, little more grinding if you go, if preferred orientation is going, means that is fine, no problem. But even after grinding, they are growing in only one direction, means that is property of your material. So you have to interpret the material growth in one particular direction only. Like now people are growing like cabbages, flowers, these kind of things are there. Why it is growing, what is the kinetics which makes that zinc oxide grow like a flower or grow like a lotus, that has to be explained. For them, the diffraction is going to be like this. Every peak will have different intensities.
Okay, sir. Sir, can we find out there is a porosity depending upon the data?
Yes, sir. Porosity, yes, there is a small amount of calculation is necessary, provided you now porosity in the material, not in the sample.
Yes, sir, on the material itself. I'm asking, sir, with the Excel data, can we find out is there a porosity or not using the only Excel data?
That is difficult, sir.
Okay,
because
sir.
the pores which are existing inside the material, they are not going to contribute for diffraction. They are just voids. So X-ray diffraction thinks that those are defects, but practically material itself is a porous material. So we can't get that porosity.
Okay, sir.
Sir, regarding Williamson-Hall plot.
Yes, ma'am.
Hello, sir.
Yes, ma'am.
How to choose the points, sir, data points? You said that to calculate the average crystallite size, we have to choose the lower peak. Instrumental broadening is small there.
Yes,
so if you have to plot the WH plot, that is Williamson-Hall plot,
yeah,
we have to be specific in choosing the points,
no,
the
no,
2 theta value.
No. In the Williamson-Hall plot, you don't have that liberty to choose only one point. Minimum, you have to take 4 or 5 points.
Okay, sir.
4 or 5 points, then only you could able to see the trend. But Williamson-Hall plot, you have to choose the family of planes. Let us suppose you start with 100, then it goes 200, 300, 400. Those planes only you can take.
Oh, okay, sir.
You can't take all the points.
All the points we should not take.
Yeah, ma'am. Family of planes, if you can take, it gives. That's why in Williamson-Hall plot, whenever you see in a journal article, there will be 4 or 5 lines they would have plotted. That is for different families of Miller indices.
Okay, sir. Okay, sir.
Yeah, ma'am. But what I mentioned was it is for the Scherrer formula. Scherrer is going to take very gross approximations. The best one is to take that lower angles, that peak which is around between 20 and 30. If you have a peak, that peak you can take, where your instrumental broadening is going to be very, very small.
Then strain is for that family alone, that planes alone, no?
That peak alone, yes, ma'am.
Yeah. Okay, sir. Thank you, sir. And crystallite size is also for that family alone.
Exactly, ma'am. That we can't attribute for the entire sample.
Then we have to calculate the average, means we have to plot for all the families, all the peaks.
No, ma'am. No.
Family of peaks.
No, ma'am. You can't do that because if you separate the analysis for each and everything, it means each and every peak, that particular value itself is average crystallite size.
Yeah. Okay, sir. From this plot, sir.
You mean Williamson-Hall plot?
Yeah.
Yeah, from
that intercept
Williamson-Hall
will give the average crystallite size.
Yes, that is average crystallite size only for that family of planes.
Okay, sir. Thank you, sir.
Yeah. If you want a full analysis, you should go for whole profile fitting.
Whole profile fitting.
Yeah, whole profile fitting like a retweet. You can do from where you can get the peak broadening for every theta. Every theta you can get the peak broadening and you can do the calculation.
Okay, sir. Thank you, sir.
Professor, I have one more question.
Please, sir.
For Scherrer formula, yes, you told that for K value it is 0.94 for spherical. So what about for different sizes, for different shapes? So what we should fix the value for K?
Because that's what I mentioned you. There is a safest way is using 0.94 as Scherrer constant because that is suitable for spherical crystals. But there is a huge debate is there how the shape is going to change the Scherrer constant. That is very tedious job to do, sir. Or else if you don't like this 0.94, you can just use 1. Mostly that is a heavy approximation. It's not going to change the life much. This is 0.94, you can use 1. But when we are using this tetragonal or triclinic, monoclinic, like very low symmetry ones, it is safe. it is better not to use Scherrer formula for crystallite size. It's very overestimates the crystallite size. Then you will be disappointed. Better you can go for Williamson-Hall plot, where monoclinic is going to give you large number of peaks, and all of them, if you put it in one, you will get a better average crystallite size in there, rather than Scherrer's formula. Scherrer formula is more suitable for materials with cubic symmetry, like simple cubic, FCC, BCC. That much only we can go.
Okay, sir. Okay.
Good morning, sir.
Yes, sir.
Sir, I want to know that from the XRD pattern, we see that for small angle, the background is higher. Why is it so?
Background is higher. Very nice question, sir. It is coming because of.
Yes, sir. Sir, I'm from IIT KGP Chandan.
Okay. Hello. Can I answer
Yeah,
now?
sir. I'm Chandan from. Yeah, sir. I'm Chandan Pramanik from IIT KGP.
It is coming because of atomic scattering factors. Atomic scattering factors, if you have studied in solid state physics sometime in your BSc, they will be having a large intensity at lower angles, and then slowly they will fall down. That's why for all the materials, you will have more intensity coming at lower angles. This is number one answer. Number two is, you are getting the background from the glass slide, which they are using it for as a sample holder. Glass will give you a huge hump there. That is number two. Number three is, there is a possibility of large amount of amorphous content in your sample. These three cases, any one of them will, or all three can give you a large hump at lower values. But for all the three reasons, the fundamental behind this is because of the atomic form factors, which are going to have high intensity at lower angles. You can search on the internet sometime where what are atomic form factors and how you can look like. So for let us calculate for silicon and oxygen, you will have large size at lower angles. That is the reason.
Okay, sir. Thank you.
Next question, sir.
Good morning, sir.
Yes, sir.
Very nice presentation.
Thank you, sir.
My question is based on why we are concentrating mostly on K alpha, copper K alpha 1 for determining crystal structure and X-ray diffraction analysis. Based on their energies or any other reasons for it?
Why only copper alpha? You mean you want to use alpha too?
Yeah. People are mostly in the almost all the X-ray diffraction instruments. People are looking for only K alpha 1.
Yes, sir.
Yes.
You can use any of these wavelengths, sir. There is no restriction.
Okay.
But copper is the one which is you can get it very pure.
Okay.
Very easily you can purify it compared with any other things. But there are diffractometers where we use silver, we can use molybdenum, we can use cobalt, we can use chromium. All those things are there, but they are costly just because purifying those materials is difficult. That is number one point. Number two is the wavelength for copper is 1.5406. This is the one which is going to give you the peaks spreaded over throughout your 2 theta value, entire 2 theta range. Now, as I mentioned in the previous for another question, the optical grating experiment, when you reduce the wavelength, what happens is all the peaks will come close to one place. Like if I use a molybdenum wavelength, which is 0.7 angstroms. All the peaks you will measure just between 20 and 50. N number of peaks you have, all of them will come there, which means it will measure things at lower values. Chromium is the one which is going to spread your peaks much longer places. So based on the requirement, people have chosen copper is the best, which is in the middle, 1.5.
Okay.
Which will spread the peaks throughout. You have the measurement range. Usually the regular lab diffractometers span from 10 to 120.
Okay.
So copper is the best.
Okay, sir.
Yes.
Sir, one more questions from the participants.
Yes, sir.
I have taken in the chat box.
Tell me, sir.
Can you comment on JCPDS?
You want a
Like
good
that,
comment or bad comment?
yes, sir. Because people, the person, the participant can ask in which way it will predicted information about samples.
Oh, JCPDS is not prediction, sir. JCPDS is purely depending on experimental results. Even you can submit your result for JCPDS. If I measure, I can submit as a entry for JCPDS. It is the standardized data. It is experimentally given. So there are no predictions in there. I have a sample, I measured it, and I submitted. That's all. So it's like a peer, you have a senior who have already measured the data. Then if you want to compare with his data, you can compare. That's all.
Okay, sir. Okay. Thank you.
But if you want the actual question, what is behind the whoever has asked, there is something called ICDD. Okay, so that is a Council for Diffraction Data, where they talk about single crystal data, where they create CAF files, crystallographic information file. That is the standard, where they have solved the structure and determined the Bravais lattice. JCPDS is just experimental data, whereas ICDD is also experimental data, but they have solved the structure. So there is, before we do this X-ray diffraction, people used to go for single crystal diffraction, and they defined the structure that the people call it like structure solution. You have to solve the structure. But now we know there are everything about 14 different Bravais lattices and everything, but before to that, people don't know how many different crystals are there. So at that time, all those methods fit it into structure solution. So that data is ICDD. That is also another database. You can get all the data. So that is single crystal data, you will get it. But whereas JCPDS, you will get a standard powder diffraction data.
Good morning, sir.
Very good morning, sir.
It was an excellent presentation, sir.
Thank you, sir.
Sir, I have a question.
Please, sir.
Sir, am I audible?
In between, something is missing, sir.
Okay, okay, sir, no problem. Sir, in literature, I could see for some samples, people are using aluminum K alpha wavelength also. Why it is preferred for some samples? The reason, Professor?
Aluminum, it must be silver, sir. Aluminum is difficult.
Okay, okay.
Because aluminum energy is going to be very, very small, then its wavelength is large, extremely large, then it won't be suitable. If it is silver means, I can give you a very good answer for that. There is another analysis type in the X-ray diffraction itself, where we talk about pair distribution function analysis or pair correlation function. This is actually developed for studying liquids. What is the diffraction comes from the liquids, and the liquids will not have long range order. They will have only short range order, which means their first neighbor and the next neighbor. That much only they will have. So there you can't use the 2 theta kind of measurements. There people will go for wave vector lambda. As I gave you this q is given as sine theta by lambda. So if you have a very small wavelength, then your wave vector is going to be very, very large, 1 over lambda. Then we will have the measurements which will have more resolution. That is altogether another different story. So that is the reason where they use silver and molybdenum.
Okay.
And especially silver targets people use in XPS, which has a very small wavelength, means high energy. You can use for any material to bring out the electrons from their core energy levels. That is my understanding, sir. If there is a aluminum cathode, then I am not aware of. So I am sorry about that.
Okay, thank you, Professor. I have one basic doubt actually.
Please, sir.
So from the X-ray diffraction pattern, how it is possible to distinguish samples, whether they are mechanical mixtures or composites or alloys? Is there how we can distinguish, sir?
Largely, there is no straightforward way, sir. Until unless you don't know the history of the sample, it is difficult.
Thank
because
you.
If you get the geological sample, it contains all the peaks. You never can figure out from what sample the data came.
So then, is there any other method to see whether really there is it an alloy or it is just a mixture? That how come we come to know, Professor?
True, sir. Means I will put this question in a little different way. The way means, let us suppose, sir, we are using an alloy of copper and zinc. This is textbook example, which means few percentage of copper, let us say 50% of copper and 50% of zinc is there, and it will crystallize in cubic system, FCC, it will crystallize. So in the full unit cell, some of them are going to be copper atoms, some of them are going to be zinc atoms. So if you see the composition when you are changing, you can obviously will from one side it is copper, other side you will be having the zinc. Then obviously you will see the changes in their intensities, peak positions and peak intensities, because copper and zinc, they are going to be 2 different atoms. However, in this case, copper and zinc are going to be very near to each other. One is 29, another one is 30, just 1 electron difference. So X-ray diffraction may not be able to show you a large difference in the intensities. But whereas when structure is going from order to disorder and again to the order state, that intensity variation we can see. That is in the alloy case. When it is a mixture, as I gave you previously, cerium oxide and zirconium oxide, those two are 2 different mixtures. If we could able to replace the cerium atoms with zirconium, then it becomes a kind of an alloy. We have doped it. But cerium oxide is cerium separately, zirconium is separately sitting the zirconium oxide, but still the both are there inside the material. We can very well distinguish from X-ray diffraction, and we can quantify how much of cerium oxide is there and how much of zirconium oxide is there. And even if you add 1% of zirconium, 2% of zirconium, that can also be very well we can quantify from X-ray diffraction. That is something called quantitative phase analysis we can do, sir.
Okay, okay. Thank you, Professor.
Good morning, sir.
Yes, ma'am.
Sir, this is Sudha from SRM. I
Yes.
have one doubt. In XRD analysis, I have chosen one parent compound.
Okay.
When I add some dopant in that compound, in XRD, I have find some secondary peak in that graph, sir. It's
Okay,
what is the reason for that, sir?
It could be the same because the same material is still, it is not become a dopant. It is still existing as the same phase, number one. Number two is there is another symmetry is picking up, because a new line has to come means a new set of lattice planes has to develop. A new set of lattice planes are coming means a new crystal structure is just started coming up. So you have to heat treat it more and measure it again. If it picks up, then you say that completely new phase has come. And if it is completely dying down and merges with the background, then your atom, whatever you have substituted, it has entered into the lattice. Now you have to see the other peak intensities. Without this dopant and with dopant, is there a change in the intensity? If it is change in the intensity, keeping all your experimental other parameters the constant, then we could be able to say that the dopant has entered into the lattice of your host. Otherwise, it stays outside as a different phase.
Yeah, okay, sir. Thank you.
Yeah. Any other questions, sir? Then there are.
Sir, good afternoon, sir.
Good afternoon, ma'am.
Sir, I am Shakuntala Devi from Namakkal, sir.
Yeah, ma'am.
Sir, I am doing my PhD work in single crystals, sir.
Okay.
Using this Debye-Scherrer formula to find crystalline size of single crystals also, sir.
No, ma'am. Single crystal, how you can calculate crystallite size from single crystal? It is already really huge. Single crystals means,
because we are taking powder XRD pattern to single crystals also, sir.
One second, ma'am. When you are taking a powder diffraction for single crystal means already you would have grinded it into powder.
Yes, sir.
Then it is no more single crystal, it is powder.
Okay.
Usually when people grow crystals, like tomorrow our Dinakaran is going to present that, they are going to grow very large crystals in centimeters, they will grow usually.
Okay.
And very difficult crystal means at least they could able to grow, if it is some perovskite crystal they are growing means they will grow in
Yes, sir.
millimeters. So there is no point comes for crystallite size there. That is one full crystal which has grown in one particular direction. It is in
Okay.
Yeah, but if you are using powder diffraction means you have already grounded it. It should be below 40 microns. Then it is just, there is no point in calculating crystallite size.
Okay, sir. Okay, sir.
The entire crystallite size is because of your grinding. You are good in grinding, they will become nano also. That's all.
Okay, sir. Thank you, sir.
Yeah, ma'am.
Sir, I have a question, sir.
Please,
I am Dr. Shankar. Sir, I am Dr. Shankar Narayan from Department of Physics, SARASWATI College, Perungudi, Madurai. Sir, is that possible to do three-dimensional X-ray crystal structures? It's not a crystal structure from powder diffraction. Suppose if I want to decipher the three-dimensional structure of molecules, is that possible to use powder diffraction to decipher those structures? Because you know that all molecules are crystallized, right? There are some difficulties if you want to get a single crystals.
Yes,
in that case, one would go for powder diffraction, and because you are telling about the determination of phases from the peaks.
Yes.
So because if you want to know the position of atoms, you have to have the phases. So
Yes, sir.
is that possible to determine the three-dimensional structures through powder diffraction?
Yes, sir.
If
Very
at all,
much
how
possible.
naive is that the technique?
Yeah, yes, sir. You have to first go for if your molecule, whatever molecule you are working on, if it is a known molecule, means you will already have a crystal structure. If you don't have, this is the first time we have grown this molecule into a crystal, means we should go for structure solution.
Okay.
That structure solution is like first you measure the Lave patterning and then go for uh, the Pearson patterns. Then it is altogether different story. My best suggestion is use a synchrotron, then you will have much better results.
Okay. As far as a single crystal is concerned,
Yes, sir.
Is that one? But my question is that possible to do to solve the X-ray structure using powder diffraction?
Yeah,
That is
yes,
my
sir.
question.
Yes, either it
Okay.
is powder or single crystal. Either way, you can solve the structure. No issue.
Oh, okay. Okay, sir. Thank you very much, sir. Thank you.
So good afternoon, sir.
Good afternoon, ma'am.
Sir, I am Sabari.
Yes, ma'am.
Sir, how you are applying the patterns, sir?
Ma'am, you are asking about patent?
Yes, sir. Yes, sir.
I am nowhere.
I synthesized crystals,
Okay,
and so after the solving diffraction single crystal diffractions, I got new crystal structures.
Okay, ma'am.
How to apply the patterns, sir?
Patent for single crystal growth, the regular patent, ma'am. You can approach the intellectual property from your university. You can apply for whether it is you want to apply any for the Indian government or US, whichever it is, intellectual property, you can directly apply.
Okay, okay, sir.
And there is nothing special, ma'am, but you will get more weightage if you could able to publish this in ICDD, International Council for Diffraction Data. Yeah.
Okay, sir. Okay, sir. So suppose how I check the new compound?
We need to buy the database, ma'am. There is no other way.
Crystal database, sir?
Yes, ma'am.
Yes, sir. Okay,
Either
sir. Thank you, sir.
buy from CDC or some place we have
CDC.
to buy. Yeah, ma'am.
Yes, sir. Thank you, sir.
All right. Yes, sir. Any other questions, sir? So, Dr. J. Kumar.
Check the chat box. One or two questions are there.
Oh. We will include now.
So without having this EAF data, is it possible to index the diffraction peak? The madam has asked, I think.
Yeah, yes, sir. We can always index it, but that's going to be like trial and error because we don't know the lattice. Until unless we don't know the lattice, it is difficult to index it. But when we go for small calculation for cubic ones, it is very easy to do. But if we go a little beyond tetragonal, we have to use a computer. But always we can generate using our known knowledge, because once it becomes tetragonal, A, B are same, C is going to be different. And if you continuously change these values at one point of time, obviously we will generate a spectra which is exactly matching with our data. So then we can say that that is one of the solution for our crystal structure. but whether it is correct or not, a little difficult, because any combination, because we have two values, A, B and C, which are going to vary continuously, which one is going to fit ours? Still, it can be done. The guy called Brain Toby, Brain, B-R-A-I-N, Brain Toby, he has made, it is written CMR tools. You can search on the internet and you can download, where you can do all these kinds of simple calculations. And without CAF information, still you can find out what kind of crystal structure your sample have.
Okay, sir. Yeah. There's another question. I am getting doublet peak. What may be the reason?
At which angle, sir?
Not given. The question is just, sir, I am getting doublet peak. What may be the reason is the question asked.
Yes, sir. The doublet is because of just alpha 2. If the diffractometer is having alpha 1 and alpha 2, then the next peak is coming because of alpha 2.
Okay.
And we have to check whether the diffractometer is using some filter kind of thing to readily strip down the alpha 2. If it is not stripping, a doublet is because of alpha 2.
Okay. Question was there. Why are you using 2 theta on the x-axis? Somebody has asked that question. Why use 2 theta in the graph on the x-axis instead of theta?
Oh, you can use theta also, but the trouble is the answer lies in the very basic geometry of diffractometer. Let me show you that. Yeah, here if you could able to see, this is the angle of X-rays. If the sample is not present, the X-ray will travel like this, straight line. Okay, sir. So, but detector is here. So if it is traveling like this without diffraction, then this is the theta. And if we have a normal over here, that is also another theta. Together we will be measuring 2 theta. So always a detector will be running double the theta. So that's why it is 2 theta in the x-axis.
Okay. One more question. Can we plot a Williamson plot for nano-composite materials?
Yes, sir. We can plot. There is no issue with that. But the limitation of Williamson-Hall plot is you have to use same family of peaks. If you can choose that, always we can plot.
So these are some of the questions which I saw in the chat box. Very, very good, nice presentation, sir. So, Kumar.
Here, I just want to clarify, sir, when they say nano composite, some people which I come across, this nano composite is coming from, there is a polymer, and inside the polymer, they are adding the nanoparticles. So for that kind of a material, if your polymer is not contributing anything to the diffraction, yes, you can use it. If your polymer is contributing to the diffraction, it is also shows some peaks, then it will be difficult to interpret which peaks belongs to the nanoparticles, which belongs to the composite, the polymer. It is very difficult to distinguish, and we can't use the, without ambiguity, we can't use the Williamson-Hall.
And then another question, is there was any free software to index the powder diffraction data?
Yes, sir. There are a lot of peaks are there, which lot of softwares are there. You can find all of them at one place. If you can search something called CPP14.
CPP14,
CPP14. That is the site name. where they have everything. And
Oh.
if you want to pinpoint, there is something called powder X.
Okay.
Only for indexing means you can have powder X.
Okay.
This program is something like a Swiss knife. Everything is there in that.
Okay.
You can always use that.
Okay. Thank you, sir. Thank you. Thank you very much.
Very much.
So, Kumar.
Sir, Kumar, sir.
Yes, ma'am. Yes, ma'am.
Karpaka, ma'am.
Yeah, one more question I am saying, sir. It is crystallite size is larger in TEM analysis from the one which calculated from XRD. Yeah, when we go for this TEM analysis, the TEM operator has to see, they will try to put this round circles around the crystallite sizes and then they calculate. If they don't distinguish those boundaries properly, obviously we will have this trouble. That method is wrong. Usually TEM gives distribution of size. It is not one single size. You should be measuring it like a distribution. They will draw one single line and then it gives that distribution, as I shown in one of my slides. That distribution only can give.
Okay.
Yeah.
Okay, Sudha, proceed.
Sir, thank you, sir, for your nice presentation.
Thanks
now
for your
we have come to the end of this session.
Sir.
Now I invite Dr. N. Karpagam to deliver the vote of thanks to the session. Ma'am, please.
Okay, sir. Good afternoon to all. Respected and our most distinguished research person of the day, Dr.Uma Mahendra Kumar, sir. Respected Chairman, respected Vice Chairman, sir. Respected Secretary, sir. And respected Principal, sir. Respected Dean of Physical Science, Dr. V. Venkateswaran, sir. Faculty members of Physics and Chemistry of SREE THYAGARAJA College, Pollachi, and research scholars, faculties, students, and friends of other various institutions who have participated in this FDP program. A very good afternoon to one and all. I deem it as a great honor to propose the vote of thanks on this memorable occasion. First, my sincere thanks to Chairman, sir, Vice Chairman, sir, Secretary, and Principal, sir, of SREE THYAGARAJA College, Pollachi, for providing the opportunity to organize this faculty development program. Next, my heartfelt thanks to Dr. V. Venkateswaran, sir, Dean of Physical Science, SREE THYAGARAJA College, Pollachi, for his guidance and support in all our activities. Ensure that we always do the right thing in the right way. Next, I would like to convey my special gratitude to our respected and distinguished research person, Dr. Uma Mahendra Kumar, sir, Assistant Professor of Physics, School of Advanced Design, VIT University, Vellore, for giving valuable information about nanomaterials, nanostructures, use of X-ray diffraction and analysis of it, and characterization of nanomaterials, and so on. Clearly clarified thank you, sir. Then I would like organizing this program and making it a grand success.
Is it over?
Sir, over, I think, sir.
Thank you.
Okay, you can close.
So once again, I thank you all the participants who have joined to this faculty development program from various institutions across the country. And now we will meet again tomorrow exactly by 10 a.m. for the second session, and which will be delivered by Dr. Dinagaran from St. Joseph's College, Trichy. And the same link will be used for the tomorrow program also. And I request all the participants to join tomorrow's session. Before 10 minutes before the starting of the session. Thank you for joining. And the feedback link is shared in the chat box as well as in the WhatsApp group. I request all the participants to fill the feedback of today's session. That will be really valuable input for our future. And with this, I close this session.
Thank you all.
Thank you, sir. Thank you all participants. Thank you.